G'day everyone, welcome to Lubrication Experts. Today I've got a very important topic that we're going to cover because it's important to basically anyone that uses lubricants. Today we're talking about oil filtration. So most of the time on this channel, we've talked about kind of different lubricants, different applications, a lot about, let's say for example, different formulations and chemistries that go into it. Well, just as an important part of it is preserving the life of the lubricant and pulling out things like contaminants. And I think we won't have to go into necessarily the importance of filtration because everyone who's listening to this is probably well aware. But I've always wanted to get a filtration expert on here. And so finally we found the man for the job. And so I'd like to welcome John Duchowski from Hydac Filtration. So John, thanks so much for joining us.
Well, thank you very much for having me. I really appreciate it. Now that you've raised the bar so high, I hope I can live up to it.
So John's got a lot of experience with Hydac across a pretty broad range, so more or less everything to do with filtration. But today we're just going to cover some of the basics of filtration and filtration media and things like that. So I think it'd be a really enlightening discussion because I suspect there's going to be some things that will surprise me and hopefully surprise the audience as well. So
maybe a few words of introduction about myself.
Yeah, would love to.
Okay, so my name is John Duchowski, obviously. I have a PhD in physical chemistry. I have been working in industrial lubricant care and treatment for 30 years. My first 13 years were at Paul Corporation, that you very likely are familiar with. And then after I switched over to Hydac because it seemed that Hydac was more into developing and more in advancing the field of industrial filtration, and so therefore I thought it was a good fit, and it certainly turned out that way. So for 30 years, essentially my entire professional life, I have been involved in care, diagnosis, and treatment of industrial functional fluids, as we would like to call them, so hydraulic and lubricating fluids and coolants.
Yeah, that's awesome. So that absolutely confirms that you're the right man for this particular interview. I'm going to assume that everyone who's listening sort of understands how important filtration is. That's sort of like ground that we don't need to tread over again. But from your experience, and you said it was about 30 years in working in the filtration industry, is there anything like particularly, let's say, unexpected or surprising that you think that the wider industry doesn't understand about filters?
I think the industry is stuck in treating filtration as simply a mechanical separation process, as a sieving action. So basically what you have is under laboratory operating conditions, we use isomedium test dust, which is a naturally derived contaminant. It's natural, made through erosion processes, essentially silica sand. And so what we have is a dispersion of fine rocks, if you will, that do not interact among themselves and do not interact with the fluid and do not interact with the filter media. So all that happens is really a mechanical action, mechanical sieving action. So if the rock happens to be bigger than the pore, it gets filtered out of the fluid. But that is not the way it is. In fact, it's a complex interplay between fluid chemistry, various contaminants that are present, also interplay between fluid and filter media and the contaminants. And so under laboratory conditions, we essentially have the luxury of working with something that is prepared, by us for the intents and purposes of testing strictly filter performance characteristics in terms of the sieving action. But in reality, and on top of it, the Multipass test, one of the most famous tests that is carried out to assess filtration performance characteristics, especially filtration efficiency, it also insists on adding anti-static additive in order to make sure that there is no electrostatic attraction or electrostatic interference and so on. But in reality, that is not the case. So we have a multipass test with 1600 picosiemens per meter, very high number. In reality, we're working with oils that are down to single digits, 30 picosiemens, 50 picosiemens per meter. And that leads to a whole bunch of interesting effects. but I'm getting a little bit too far straight away from the main topic, and that is we have to reconsider filtration in terms of this complex interaction between the fluid and the filter media, most often fiberglass, but often cellulose, for example, contaminant. And now we have a whole range of things. We do have the non-interacting rocks, simply environmentally derived dust, but we have active metallic surfaces that are generated in the course of wear processes. We have all these other contaminants, soft contaminants, gelatinous materials that everybody refers to as varnish. I really dislike that word. It sounds technical, but it isn't, because there's many different forms of varnish and many different reasons or many different sources or reasons behind why it arises. So varnish and paper machine lubricating oils, completely different from varnish in turbine loop systems, completely different from varnish in electrohydraulic control systems, also completely different in polyolesters and so on and so forth. So this is the main point that everybody forgets. Everybody thinks that they will just stick a filter in the can and it will filter out solid particulate, but it is subject to interactions with all these other materials that I just described.
Wow, that is an awesome introduction, because I think that answer has probably opened a whole bunch, certainly opened my mind, in the fact that maybe the way that we've been thinking about filtration is outdated. I could draw a little bit of an analogy. We've always struggled a little bit in the lubricants industry. So when we talk about oil formulations, things like that, we've always struggled a little bit because most of the people that come to our industry have a mechanical background, and a lot of understanding lubricants, lubricant chemistry, lubricant degradation. You need to have a little bit of a chemistry background. And often there's not enough overlap in those two domains. And so there's a bit of a knowledge gap. As it turns out, I wasn't aware of this. That same knowledge gap probably happens in the filtration industry, or at least in people's understanding of filtration. So that's a really fascinating insight. And, there's so many questions I could ask out of that answer. But before we get into kind of the nitty gritty, I'd like to cover some of the basics on filters as well, so that everyone's on the same page. We've got different types of filters within the industry. Let's say, for example, surface versus depth media. You've got all your different materials. Could you please help run us through some of the, let's say, primary characteristics of oil filters, and then what's some of the decision points that would drive someone in the industry to choose one over the other?
Well, it's a very simple description. Surface filtration really is either membrane or metal sieves. So if you have a metal sieve, that's basically surface. There is only a certain number of pores available to you, and they are all in plane. So if the particle is impinging perpendicular to the plane, it cannot go beyond that, right? So whatever swims through the pores, and whatever gets stuck, and therefore the next particle is going to get stuck on that one, and so on and so forth. Now, you also have to put yourself in a sort of a particle space, or if you are a micrometer particle, a millimeter to you is 1,000 times larger, so it's a kilometer to you. So it's like you're walking for a kilometer, and even 1 millimeter thickness of filter media to a micrometer particle is already a kilometer long. So he's swimming along in that very tortuous path and can get stuck anywhere by various mechanisms and so on. There are three fundamental mechanisms that are operative in this environment. And so you can pack a lot more particulate, and you also can increase the filtration efficiency owing to this long path that the particle has to travel through. In chemistry, and this is a very good analogy that you brought up, you have to have a certain amount of chemical knowledge, but light absorption works along exactly the same path. So if you have one of the things that is one of the parameters that governs the amount of light absorption is the path length. So if you have a cuvette that is 1 centimeter thick, it will absorb less light than a cuvette that has 10 centimeters long. So this is exactly analogous. Now, what are the three mechanisms that I was referring to? The first one is simply direct interception. So the particle hits the fibers, cannot penetrate the pore, gets stuck on the fiber, and essentially is filtered out. The second one deals especially with small particles. So they are subject to Brownian motion. So they kind of move around in any which way they can. And in the course of this Brownian motion, they occasionally impinge on the fiber and get stuck on the fiber and get filtered out. And the third one is inertial interception. And that is the fluid is going this way and then turns, but the particle is big and heavy. This applies for the bigger particles, whereas the Brownian motion for the smaller ones, particle is big and heavy, continues along the same path, gets stuck in the fiber media. This is analogous to how you're traveling in a car and you're in a non-inertial frame of reference. The car turns right, you're leaning left, but the car turns left, you're leaning right. Sorry, but this is not really what's happening. You continue on the straight line, as inertia basically says. So this is the same thing here. The fourth force would be electrostatic attraction, but in the environment that we're working with, in typically these high dielectric, highly insulating fluids, there is no electrostatic attraction because we're working in an insulating environment. So typically in liquids and high viscous liquids, already starting with, let's say, 15 to 32, 68 centistoke oils, only the direct interception is the one that plays a role. The reason is that it's very hard for the small particles, even for the small particles, to penetrate against the viscous drag and against the viscous force operative within the fluid. And it's the same for inertial impaction. They do tend to travel with the fluid because of the viscous drag upon them. But sort of a quick rule of thumb, air filtration for the same grade media, exactly the same filter media construction, fruit element construction, is 10 times more efficient in air than it is in viscous liquids. And it is exactly for that reason, that in air, these three mechanisms are all operative, whereas in the viscous fluids, only the first one is.
Awesome. Wow. Okay. So again, that brings up a whole bunch of different questions, but first would be the different materials as well, right? So we've already talked about surface media filtration. So just to, clarify the difference between surface media versus depth media. So with depth media, is the technical definition anything that's not surface media filtration, or is there a more specific definition of it?
There is again, like I said, 5 millimeter thick is already depth. Membrane, which is millimeters thick, or not even, even less than a millimeter thick. Like, think of a cellulose acetate membrane. That is strictly surface. Mm-hmm. There's really not much, and all the contaminant gets deposited on the surface. This also has to do with how tight the porosity is.
Yeah.
And there is no pore gradient, right? So if you have a 0.2 micrometer membrane or 0.45 micrometer membrane or even 0.8 micrometer membrane, all the pores are really too small for the normal dirt that we find in hydraulic and lubricating systems to penetrate and go through. So now you very quickly occlude the surface, and then you build a little bit amount of cake on the surface. So this kind of a pore gradient in glass fiber media that you have, this very tortuous path, it's not really a funnel, but you can sort of think of it as kind of a convoluted, like a little ball of cotton. You know what I mean?
Yeah.
Except that the fiber diameters are all different. That the fibers are all of different diameters.
Yeah.
And there is also a rule of thumb that says that you cannot make a 1 micron filter out of 10 micron fibers, 10 micron diameter fibers, because you will occlude the space. You cannot bring two 10 micron diameter fibers so close that you leave 1 micrometer hole in the middle. They will occlude the hole and you can't make it. So another depth yet is this completely depth filtration now. And this is extruded meltblown deposited on a mandrel. So now you have this really white looking, no pleats, but white looking candle. And this is very much depth. We were talking about 2 inches diameter or something like this. So now we have instead of few millimeters, we now have a couple of inches or a couple of centimeters. So this really is huge. And to give you another, just a quick over difference, the 5 millimeter thick still depth media will exhibit efficiencies order of 200 or 1000 at a given micron rating. That means 200 particles upstream and 1 particle downstream in a given size range or greater, or 1000 particles upstream and 1 particle downstream. These really depth media that I'm talking about, the extruded meltblown, they have efficiencies already over 5000 and higher. Very difficult to measure in the lab because you have to pack a lot of dirt. You have to first of all have 5000 particles upstream available for you to demonstrate that only one gets through.
Mm. Yeah, that's really interesting. So we've already touched on a couple of different materials that the media is made from, right? So you've already mentioned cellulose media and glass fiber. What are some of the decision points about which one to use? And are there any other materials out there that we should really be aware of?
There are meltblown materials, meaning extruded polymers. There's a whole range. There is polyester, so PBT, PET, polypropylene, polyamide 6, polyamide 6,6, polyamide 612. So you can play with all of these. But glass fiber still has the distinct advantage that you can mix and match the fiber diameters. Whereas in extruded meltblowns, this is dictated by the nozzle itself, so the shape and the opening in the nozzle, the orifice of the nozzle, how far the mandrel sits away from the nozzle, so that how far is the fiber able to grow as it's going down towards the mandrel, how fast the mandrel rotates, and how fast the mandrel oscillates like this. So in reality, it's very difficult to control the fiber diameter in meltblown materials. And this is even for this is for the candle. You can lay down meltblown materials on a flat substrate, very much like we do with glass fiber. So glass fiber is just laid down on a flat substrate, and then but you have very little option because now the belt is moving exactly under the nozzle, always the same distance. You cannot adjust for the fiber diameter. So basically, you have only the same channels, the same fiber diameter, and that gives a distinct disadvantage in terms of dirt holding capacity and filtration efficiency. So, but it has advantage of cost. So it's much cheaper than fiberglass. Meltblown materials are. So if it all depends which way you want to go. For I would say critical and difficult to handle applications. So for most of the hydraulic and systems that I know of, glass fiber is still the king. It's still the primary material that you can use.
Interesting.
Also from the perspective of differential pressure drop, there is no penalty. The penalty for pressure drop is the smallest because you can adjust this fiber matrix. You can also adjust the fiber matrix density. So you can pack more fibers in certain amount of space, and when they are packed tighter, they obviously will pose greater resistance to the fluid flow, but they will have greater filtration efficiency.
Yeah, so that's an interesting trade-off to talk about as well, because so in my head, and I've only thought about this in a very simple way, there's no I'll make a filtration joke here. There's no depth to my understanding. I've always thought of there being a trade-off as in, surely the differential pressure across a filter should simply increase as the, let's say, efficiency of the filter increases, right? Because in my simple conception of it, the tighter your kind of pore spaces are, the more dirt you're going to filter out. However, you're going to pay for that with, a delta P across the filter. Now, I'm sure that's kind of like the generic explanation, but how do different, let's say, how do the different media affect that? Because you do see some filters that don't seem to have that same sort of differential pressure rating, but they still have high efficiency. Like, how are they achieving that?
They achieve it by, it's actually not all that simplistic. It's exactly how it is. You have a triangle, and the triangle consists of the filtration efficiency, pressure drop, and dirt holding capacity. And if you tug on one apex of that triangle, the other two come in. So it is a kind of a, you can't, you only have so much pull, if you will, before you kill the other parameters. So if you make a filter much more open, exactly as you say, the DP is going to be lower, dirt holding capacity is going to be higher, but filtration efficiency is not going to be very good.
Right.
So you can play with this by essentially in two ways, and that is by selecting fibers of different diameters and then using different ratios of the same. So should I use more fine fibers? If I'm going to use more fine fibers, say, I don't want to use too many technical terms, but they are all referred to as, let's say, 106, 110, and so on. So, and typically this is diameter on the order of 0.69 micrometers and the length about a quarter inch. So I still oscillate between metric and American units, force of habit.
Yeah.
So yeah, you can pack more of these small diameter fibers. You're going to make the filter much more efficient, but you're going to sacrifice dirt holding capacity and pressure drop. Now, if you play with endless combinations of these, you can actually improve it in some way, shape, or form. And by playing with it, I mean you have to go back and think a little bit about how these media are made. So they are laid down. They are laid down in a paper machine, very much like you make paper. This is the same, completely analogous process. You have a slurry of glass fiber and a binder, and this is now sitting in a head box of a paper machine and is now being trickled down onto the substrate, typically polyester, some like Remake. And then what you do is you spray adhesive on it, and then you try to remove as much excess adhesive as possible, not so that you don't occlude any pores. And so now what happens is, if you have a machine that is more flexible, and by this I mean they have different head box configuration. So some machines have one diagonal head box and one flat head box. I've seen machines even with up to 3 head boxes. So you can now start with the lowest head box, using very, very slurry of very, very fine fibers. And then the diagonal, let's just stay with 2 head boxes. And the second head box at this angle is going to be supplying the coarser fibers. So now you essentially are injecting or building a gradient of porosity into the filter media. So there is a bit of a built-in pre-filter into the filter media construction, if you will. And depending on the fiber mixture and the amount of the different fibers and so on, you can manipulate this a little bit to your advantage. Although, there are always some points of diminishing return that when you hit, and so 1 micron element, to put it, or 1 micron filter media is always going to have a higher pressure drop than 3.
Yeah. 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 That's interesting. I've never really thought about the sort of that triangle that you described and the trade-offs that you have to make when designing filters, but that makes a lot of sense. All right. So between the different filter media, we already spoke at the very beginning about the fact that we need to sort of take ourselves beyond just a mechanical understanding of sieving out particles. So are there any differences between, cellulose, glass fiber, and some of the, let's say plastic materials, that sort of the nylon style? Are there any differences in how they interact chemically or electrostatically with the oils?
Well, in our environment, the differences are marginal. But if you go to an environment like air or polar solvents like glycol or water, then the situation becomes dramatically different. And yes, electrostatics play a role. Zeta potential, which means you can charge the filter media and you can increase the attraction between certain particulate and so on. We have done this to a certain extent, and we see marginal differences. And you start, then you enter the area of material science, where when you start with a, let's say, base glass fiber, you can adjust its surface characteristics and augment its functionality a little bit. Now, unfortunately, like I said, since we are working in a highly nonpolar environment and highly dielectric environment, this is like if you're moving iron turnings on a with a magnet, and you're separated by a piece of paper, you can move them fairly well because of this magnetic attraction. But if you put a piece of cardboard, there is not that much attraction anymore, right? The magnetic attraction between them is weakened. And so here too, only if you bring the materials very, very close to the surface and do it very slowly, where this attraction has an opportunity to materialize itself and play a role, then yes, you can make some adjustment on that level as well.
Okay. No, that's really helpful. How about some of the kind of standard industry terms that get thrown around, but maybe like some clarification on that too, right? We've already talked a little bit about beta ratio and its relationship to efficiency, right? So you described the beta ratio. So, something that's beta 1000, that really means that there's, 1,000 upstream particles, one downstream particle. So, in terms of efficiency, it's able to remove 999 out of 1,000 particles at a specific micron size, right? So, for anyone that wasn't aware, that's kind of how the beta ratio is calculated, but it's also done at a very specific micron size, right? So then one of the other terms that gets thrown out there a lot is absolute, filter rating or nominal filter rating. Are these standardized industry terms? And if so, what do they actually mean?
Well, this dates back to the time when a different contaminant used was one in all the test stands. So this dates back to the 1950s or the 1940s even, when actually Dr. Paul, believe it or not, realized that some of the aircraft that is coming back to the carriers, the undercarriage doesn't come out. And he linked that to the presence of contaminants. And so the military at that time set up a test to determine filtration efficiency, dirt holding capacity, and all these other things. And that was referred to as a MIL-F 8815. So military filter 8815. And they used monodisperse glass beads or monodisperse polystyrene beads to test the filtration efficiency or the separation efficiency of filters. And so if you challenge the filter with 3 micron beads, and they are very, very monodispersed, so the particle size distribution is very, very narrow. It's 3 micrometers plus or minus 0.01 or something. So they make them very, very precisely. So if the particle 3 micron penetrates and the 5 micron does not penetrate, well, there you have the 5 micron absolute. So, but it does not translate into any percentages, and this is important. People now make some kind of an arbitrary differentiation that 99.5 and below is 99.5 and above is absolute, and below that is nominal. No, actually, there is no definition for nominal. The original definition for nominal is that if the filter is going to filter out once in its lifetime a particle of a given size, then you can call that filter nominal this, right? So your SOx will eventually attract a particle of 0.1 micron size in dust that is floating around the house. So your SOx are 0.1 micron nominal filter. So this is where it goes back to. Now, the reason that the industry has switched to, and one more thing about MIL-F 8815, they still use the same military fluid, MIL-H 5606, so military hydraulic 5606, red dye, aircraft hydraulic fluid, 15 centistokes, and like I said, they have to additize it to 1600 picosiemens per meter to make sure there is no electrostatic activity going on. And here it's not just so clear cut that there's no electrostatic activity to help agglomerate the particles. This is also to prevent electrostatic charging and discharging. So they already knew back then that if you have fluid of low conductivity, you wouldn't be able to conduct this test because the filter elements would be arcing. Although way back when in this military application, they used only wire mesh elements. So electrostatics did not play a role. But as soon as people started using glass fibers, it did. And so to overcome that, they started additivizing the test stand with Stadis 450 to reach the 1600 picosiemens per meter. So then when people wanted to get, or the industry said, yes, but we're not working with glass beads out there. We're working typically with metallic particulate, all right, environmentally derived sand. So that would be the first thing. So instead of using glass beads, let's switch to silica sand. But then you have a very broad particle size distribution. You have a polydispersed material. And so how can you now say, and not only this, but they are all irregularly shaped. So you have particles that are thinner, skinnier, fatter, thicker. And, how do you decide that this is a 10 micron particle when it's very, very irregularly shaped? So they devised methods for either taking the longest dimension, or then later they took the average width and they drew a circle around it and so on. But now you no longer have this clear-cut absolute and not. So that's why the beta ratio came in, because it's an average amount of material that penetrates the filter. But you also have to keep in mind, and like I said before, you have to have sufficient number of particles available upstream of the filter in order to demonstrate the 200 to 1 or 1000 to 1 cutoff.
So could we please maybe back up a little bit and understand how the beta ratio test is conducted? Is that like a single pass test, or is it a multi-pass test? How exactly does that work?
It's a multi-pass test. So you have a main circuit that is supposed to establish a constant so-called bug base upstream gravimetric level of, let's say, and you have a choice of 3 by the ISO 16889 standard. You have a choice of 3, 5, and 10 milligrams per liter. And as some of it is, and so that stream carries the main contaminant load to the filter. But obviously, as some of it gets depleted by filtration, it gets re-injected. There is an injection circuit as well. So there is a metering pump that injects sufficient amount of contaminant to bring it back up to the 10 milligram per liter constant base upstream gravimetric. However, since it's a multi-pass test and the filtration efficiency is different for different particle sizes, so that's a very famous other representation of beta curves that is just a straight line for different efficiencies for different particle sizes. So it's not really the case that you have an absolute filter that, it filters everything 3 microns and above and doesn't filter anything below. It's not the case. It still has filtration efficiency below the rated beta ratio, be it 200 or 1000. So that's the reported value. But it still filters below that. And so, but at different percentages rates. So you have to then imagine that the particles in the small size range concentrate as a result of this. So the particle size distribution, though not the base upstream gravimetric, change in the course of the multipass test. And it turns out that it's mostly the fine particles that plug the filter and not the coarse. Because if the coarse particle sits on the external surface of the filter, it's just like a big rock in a stream. The fluid goes around it. But if the actual pore is directly blocked or interfered with, then the passage of the fluid is restricted, and that's why differential pressure increases.
Okay, so that's kind of gets into something I definitely wanted to ask about, which was that the beta ratio and a lot of the ways that we characterize filters, that's kind of numbers that are measured up front, but we know that filter performance changes over time, specifically with the development of a filter cake. So could we please help everyone understand, firstly, what is a filter cake, but also what defines the development of a good versus a bad filter cake and how that affects the filter performance over time as well?
Well, that's a common misnomer because there is not much cake filtration in liquids. Some, but not much. Mostly cake filtration occurs and cake filtration augments in gas filtration applications. And this is going to be a long-winded explanation, so bear with me.
Excellent. We love long
If
winded.
you look at the beta curve ratio or differential pressure that increases in the course of a multipass test, you see it's something like this. It's a quasi exponential. So it stays flat for a very, very long time, and then it turns. But in reality, what you have is a situation like this, where you have a kind of a diagonal slope line and a flat line. And if you connect the two, then you get this quasi-exponential. So the flat line corresponds to the large void volume, huge void volume being filled by particles. And the reason that differential pressure stays flat over that period of time is because you have 1 million holes, just an example, but with each pass you're filling 10. So it makes no difference for the rest of the holes. The fluid will find its passage through the filter media anyway. And then there is this cake filtration, small amount of cake filtration and liquid application, where you have this kink. And yes, you can see in certain well-constructed elements that filtration efficiency will also increase. So you can see situations where, and now for each individual particle size, you see this kind of a thing in a beta ratio curve, right? You see this kind of a flat, but then a slow increase, but it's not exponential or anything. And that means that there is an observable increase in filtration efficiency in the course of the test. Now, I've seen some filter elements that are not very well constructed, and actually you see the opposite. You see that after a certain amount of differential pressure accumulates across the filter element, there's a break, and there is a break through the filter media, and then the particles go through there is essentially migration of particles through an open hole. Now, you don't know where the open hole is. It could be between the end caps, if the adhesion between the end caps and the mesh pack is no good. It could be at the seam, because seam is a weak spot, or it could be just that there is some weakening of internal structure of the filter element. Now, so this is basically how you can tell a good filter from a bad filter. And without naming any names and going into too many details, there are recommendations out there that advise customers and end users and equipment operators to change filter elements at a very low differential pressure. 35 psi, 50 psi, so 2.5 bar thereabouts, because of this. This is a well-known effect. Now we can run our filters, and I don't want to sound commercial, up to 7 bar, in some cases up to 20 bar, without the loss of filtration efficiency. You don't get much out of it, because if you look at the deep P curve, it's like this. And if you draw the straight line down on the timeline, you don't win much by going from 7 bar to 20 bar. So it's not worth it. But, people sort of just get off on this fact that, yes, you can run the system down to that level without the loss of efficiency. Now I will transfer to the gas filtration, which is in many cases far more interesting than liquid filtration. So not only do you have cake filtration that plays a very strong role. I went into this before about the different filtration mechanisms of interception, inertial, Brownian, and electrostatic is the fourth one. But in air filtration or gas filtration, you have the additional benefit that as the cake forms around the filter, the cake actually begins to form its own fibrous structure. It grows dendrites. And so therefore the filtration efficiency increases as the filter accumulates dirt without too much expense at the differential pressure. So one very rarely monitors differential pressure in breathers, for example. In some cases, where application is critical, like gas turbine air inlet filtration, yes, you have to monitor it because you don't want to starve the turbine of air. But then you use inches or millimeters of water column, because the measurement has to be that sensitive. because otherwise, if you use mercury or something like this, then which is a normal differential pressure scale, you wouldn't see any differences over the even when the filter was, let's say, sending only 80% of the initial air volume through. So that's why you need water column measurement.
Wow. That's an interesting insight that I had not anticipated. But I guess one of the questions that I certainly have, um, as someone who uses filters, right? Filters, even just over this conversation, has gotten way more complex for me than I had ever imagined, right? So it's a combination of trying to find the right beta ratio, the right dirt holding capacity, something which is going to maintain its efficiency over time. We've got different um, fiber materials, different weaves. Um, with all that complexity, how should a consumer, whether on the business side or just as a consumer, how should someone go about selecting a filter from all these different variables?
Well, there are two approaches to this, and from my perspective, one is less preferred and the other one is more preferred. And the less preferred is where the customer or the end user or the equipment operator imagines that he knows what a perfect filter is, and he gives you a spec for this and says, fulfill this spec. And the right way to do it is to ask us to give us basically system operating parameters and operating components, and basically ask us to recommend what would we think as filter experts would be the best filter for the application. And to put it in sort of colloquial terms, the first one is you come into your doctor and you say, Doc, I want my right kidney out. And if the doctor just wants to please you and satisfy you, he says, hop on the table, and I get right down to it, and out she comes. The good doctor will say, hold on a second, wife, is this really what you want? Because I haven't even examined you yet. I don't know how your system works. And it may be that the right kidney is not the problem here. You know, it may be your right toe or left toe or something that is just projecting the pain onto the kidney. Another one that I can give you, which is also equally applicable, is that if you come to a restaurant and you order a cheesecake with escargot or snails on top of it, and the waiter is going to say, sure, if that's what you want, that's what you get. And, chances are you're not going back to that restaurant anymore.
Yeah, that's a good analogy, actually. Um, I like that. I really like
I've
that.
worked on a number, sorry for interrupting, but I've
No,
worked on a number of cases where, and particularly the OEMs are of that mindset that since it's their piece of equipment, they know better, and they give you the spec on a piece of paper, and then we, jump through the hoops to satisfy it, and then we find out that, most of it, if not all of it, was wishful thinking on their part, and it just doesn't work in practice. And so, they get under a lot of pressure because they selected a supplier that apparently doesn't know what he's doing, although we fulfill their spec perfectly. And then we are also racing to fix the problem to remedy whatever the situation is. And this is when you find out really what their key parameter is. And in 99% of the cases, the key parameter is service life. People can deal with slightly dirtier oil. The equipment doesn't break down immediately when you're going one ISO class higher or two ISO classes higher. It's all that sort of a perception. But the most important thing is if you have to park your vehicle on the side of the road because differential pressure indicator is telling you that the filter is clogged or is exceeding the terminal differential pressure, that is what really brings pain to the operator and the OEM. So then you have to say, okay, what happens if we back off a little bit on the filtration efficiency, and instead of beta 5, we go with a beta 7, and it's possible to monkey around with the fiber structure to achieve that, although the differences may appear small, but you can shave off the offending differential pressure and allow them to achieve what it is that they want to achieve.
yeah, that's really interesting. So maybe another kind of consumer oriented question as well. One thing that we've seen in the bearing industry over the last decade to 2 decades is the widespread use, unintentional, the widespread use of fake bearings, right? So, you know,
Of what
knockoffs,
bearings?
fake bearings. So it'll be, it looks like, SKF or an NSK or an NF or an FAG bearing. And we find that it's been, manufactured in another part of the world and just made to look. And the fakes are very convincing to the point where, the bearing companies now have their own apps where you can kind of scan, a QR code or a barcode or something to verify the authenticity. Is that something that you've seen in the filter industry? Because that's something where I can imagine, you would end up with, poor quality product masquerading as some of the major brands.
Ubiquitously, all over the place. And we've seen counterfeits that were initially made to from afar, couldn't tell the difference because the printing on the box was the same. One letter, like D in our particular case, was turned backwards. But if you're looking at a shelf with 20 cases, most of them actually edge on, not side on, then you don't really care. Then they stopped even doing that, and they just started printing, the Hydac and whatever. And then they got to the point where they even started printing "Made in Germany" on the end caps. So I've seen a situation like this in Australia, actually, where we proposed a certain very highly specialized filter element to a power plant, and because of the price, admittedly was higher than normal. But this is an element that eliminates electrostatic discharge, and they had a severe case of that going on. They ended up not getting it from the original source, but just sourced the part number on the market. And they came back to us complaining that we had 3 teleconferences and you promised us to solve the problem. And here we are, we're back to square one, exactly with a part number that you recommended us to get. And we ended up doing material analysis, and we ended up getting the cartridges, and they were not manufactured by, we have only 3 locations in the world that manufacture filter elements. And for these particular ones, they are only manufactured in Germany and the US.
Yeah.
But it's a severe problem coming from everything. This is a sophisticated example of a very niche issue. But again, when we talk about this terminal differential pressure, if we put in the catalog stable to 20 bar, even 10 bar, say, burst pressure, and the thing explodes on you after 5, it's not really something fun to live with.
Yeah.
Because then a fake filter element ends up in your fake bearings.
Yeah. Yeah. It's just fake on fake, isn't it? And that's something that, hopefully we can raise a little bit of awareness, because I think that's something that a lot of, certainly my customers are unaware of when I kind of raise it is, do you know the provenance of, I think everyone seems to be well aware of the bearing issue, but people don't seem to take the same kind of care and attention when it comes to filters. It looks like a filter, it smells like a filter, it must be one. But
does it quack like a filter?
Yeah, exactly right. So that's the thing. If just raising the awareness that making sure that we are actually purchasing through the right channels to make sure that we're getting the quality products that we're expecting is something that I kind of want to ask about. Now, as we kind of wrap up these discussions, I always like to ask a question about what is the future of the industry. Now, in the case of filters, it seems like the future is kind of here now when we have the discussion about ESD, which you just raised, right? That ESD is something that was known a long time ago when we talked about the mil-spec testing and having to raise the conductivity of the fluid because of their awareness of the ESD. That obviously is, I would say, maybe the awareness of the problem is greater now. Partially because the fluids are changing as well, right? Everything gone to
Well, you don't want to raise the conductivity of the fluid. That's actually the wrong way. You want to stop the filter element from charging the fluid. So the onus is on the filter element. The conductivity of the fluids is going down actually
Yes.
rapidly.
Yeah.
Because of that higher.
What I meant to say was that the mil-spec testing was raising the conductivity on purpose. The trend in formulations, as we're starting to remove, metals from the formulations and everything, the trend is for conductivity to go down. So that's placing, more emphasis on the role of the filter. So could you please describe basically, what the role of the filter is in ESD generation, and then how do we what are the techniques and the materials that we're using in filters to help reduce the issue?
If you look at periodic table of elements, everything on the lower left is charging positive, and everything on the upper right negative, right? So if you bring these two bodies together, like sodium and chlorine, one of them totally gives up the electron and the other one takes it. So you have an ionic bond and you have an Na plus Cl minus outright. Everything in the middle depends on the differences in electronegativity potential. And if you look at the old Alessandro Volta cells, if you had copper and aluminum and you put them in an electrolytic solution, you would have a spontaneous flow of current. So now we go into the semiconductor world, insulator world, which is where filter media are and where the oils are. And so you have the same thing where you have one electron donor, this being a glass fiber, and one electron acceptor, this being the oil. So the glass fiber charge is positive and the oil negative. There is no flow of current because oil is also an insulator. So you basically have a dielectric separating the two interfaces of this diffuse double layer. And when when the electric potential exceeds the dielectric breakdown strength, there is a discharge occurring and you have an arcing in the fluid. So the role of the filter element this is actually fundamental. It is what charges the fluid. And this is something that, always before that was a game that filter people played with the fluid people and, pointing fingers, no, you fix the fluid, no, you fix the filter. But the physics tells us quite clear story. It is the filter and you have to fix the filter. And we found the way to fix the filter, and it's described in our article in Tribology Transactions published last year, for which I'm very happy and proud to say, awarded an Edmund E. Bisson Award for the best written article in published in TLT, not in TLT, by Tribology Transactions the year prior, which basically describes the fundamental physics. And you're right, the problem has been known for at least 20 years, but we didn't figure out the fundamental physics until about 5 years ago. And from that point on, we started tweaking the modification of the filter media in order to keep improving it and to keep adapting it to various fluids and to adapt it to even lower and lower conductivities. And one of the most interesting examples was gas to liquids, and we still managed to fix it. Gas to liquids in some formulations exhibit conductivities of 0.8 picosiemens per meter at 15 degrees C. So, to come up with a formulation that you can tweak to meet that operating, performance is something special. But once you figure out the mechanism, you know in which way in which direction you need to move. And going back to your sort of a bit of an earlier question, maybe this would be a good way to conclude by describing the future. And there are two ways of looking at it. So either people will go into the commodity market and they will, do the Walmart thing. And I'm nothing against Walmart, but you buy a bag of socks for $10 and they were out after 3 days, and then you go and get another one. Or you buy quality socks and they last you 3 years, So, and they do the job. And, they keep your feet warm, they don't sweat and all of this kind of stuff. So it's the same thing with filter elements. And I think, now that we have touched upon this material science side of things, where we understand the interplay between the carrier phase and the dispersed phase and their interaction with the filter media. We have opened up the gates here. We can tweak the surface of the filter media such that that the adhesion between select contaminants is higher. So if we know that metallic particles are of interest here because there's a high degree of wear of mechanical components, we can selectively filter out the metallic components, but leave the other stuff behind. If we deem it not to be too harmful to the system, not hard abrasive materials, obviously, but something like this. Then it's possible now that we also have that's established this for other fluids, more polar fluids, water, glycols, water alone and water glycols, polyalkylene glycols, and all this. You have an opportunity to tweak the filter media to achieve optimal performance characteristics, be it filtration, dirt holding capacity, or whatever, depending on what the fluid and what the system is, or what the system generates, or in which environment the system operates. So on going along that, we also designed in much improved phase separators. So for example, liquid-liquid coalescers, where we have a muchly improved, much more efficient water separation from oil, where we don't need a separator cartridge. The normal configuration is you have a coalescer and a separator. Whatever the coalescer shakes out, the separator stops. But actually, we have an inbuilt coalescer drainage layer such that you don't need the separator. It's so efficient in knocking water out, and it's also efficient in knocking water out in more difficult environments like morgoils. So, and application of coalescence, because of the phase velocities not being amenable to high viscosity fluids, 320, 460, 680 centistokes was unheard of, and yet we can tackle the problem successfully nowadays. Improved filtration efficiency for dust from gas turbine air inlet filtration, by modifying surface characteristics and increasing the adhesive forces between silica sand, which is essentially the predominant contaminant, or alternatively also salt crystals if you happen to be on the ocean shore or something of that sort. So this is where it's going, in my mind. But then obviously, you're building a pyramid here, and you're on the very tip of the diamond corner of a diamond. So it requires much more sophisticated marketing technique. It requires much more dialogue with the customer, and the proof is in the pudding. So it requires you to provide appropriate backup in terms of laboratory evaluations, in terms of on-site field evaluation, so that you can prove it. And this is why for electrostatic discharge, coming around full circle, we have built portable measurement systems that we can take on site and show that, well, depending on the filter construction in your environment, Mr. Customer, the standard filter generates 12 kilovolts and ours generates 2 or 4, and not kilovolts, but volts. So we have orders of magnitude change here and orders of magnitude increase in protection. So I am always on the side of better technology at higher price, but you pay what you get what you pay for, and otherwise there would be no Porsches and no Versace ties around.
Yes.
But so that
Yeah,
would
wow.
be
Well,
and being a science weenie, I find that approach a little bit, I hate to use the word, but maybe not. I shouldn't use the word sexy anymore, but enticing and appealing. Let's say that way.
yeah, wow. That is that is a promising future, and I think part of the excitement of my job is I get to see that different parts of our industry are really pushing the boundaries into places that we probably never really expected them to go. So, Dr. Duchowski, honestly, the past hour broken up into 2 sessions, I think I've probably learnt more in that hour than I have talking to anyone else, which is definitely not to throw shade on anyone else, but just filters is just one of those areas where I think there's a lack of knowledge, even more so than in lubricants. And so getting a fuller understanding of new filtration technologies and even some of the basic, physical characteristics of filters and filter media and how filtration occurs has just been so valuable for me and hopefully for the audience as well. So, Dr. Duchowski, thank you so much.
Thank you very much, Ralph, and looking forward to and many more to come if should you decide to pursue it. All right.
Definitely.
Have a good one. Thank you. Take care. Bye-bye.